Hello, so in this video we're going to start looking at second order ODEs. So we've looked at first order ODEs. Remember, first order ODEs is just a differential equation where the highest derivative is the first derivative, so we call it first order ODEs, okay? But now what we're going to start doing is looking at a differential equation where the highest derivative is the second derivative, so therefore it's going to be the second order. Okay, because it's a second derivative. Okay, and in general, we're going to look at it sort of this form. So we're going to look at it with variable coefficients, although we could equally have constant coefficients as well. Okay, plus b of t y equals some function involving t. So in other words, these are our coefficients a and b, and they can both vary on time. So they could be things like cos or sine or e to the t or whatever. Okay, but the point is the highest derivative is the second derivative. Okay, and it's just basically, it's just basically a differential equation. So it's an equation which not only involves a function, but also its derivatives as well. And the highest derivative of that function is a second derivative. So therefore, it's a second order differential equation. Okay, and we're going to first of all start looking at the case actually where we can reduce this equation down. So given some special conditions, we're able to reduce this equation down into a first order ODE. So in other words, where we only have to consider the first derivative. Okay, the first derivative. The first derivative, okay, and that's what we're going to look at first of all. So let me just show you by example. I think it's easier to just see it by an example rather than talking generally, because that's at risk of confusing you. Okay, but I'll try and explain it as best as possible. So first of all, I'm going to look at this case. Y double dash plus y dash equals e to the minus t, and we're asked to solve that. Now, whenever we're asked to say, the question might say, for example, solve this or solve this. If I can spell it, never mind, that'll do. Solve this. Now, all that basically means is find out, well, what function works. So what is the function which, when we plug it into that equation, will work it, will satisfy it. So the left-hand side is equal to the right-hand side. That's all solve basically means. Well, look what we have with a general second-order differential equation. When we have general order, second-order differential equation, what do we have? So this is sort of everything that we would have in a second-order differential equation. We would have the second derivative, that thing. Okay, we'd also have the first derivative, that thing. We'd also have the function itself. So if you like, that's the zeroth derivative. If that's the second derivative, that's the first derivative. That's, if you like, the zeroth derivative, just the function itself. And we'll also have some function involving t on the right-hand side. Okay, so, sorry, no, that's not that. So some function involving t. So that's generally what we will have with the second-order differential equation. The second derivative, first derivative, the function, and some function which is involving t. So that's what we call the independent variable. This function involving t is, if you like, the independent variable function. So it's not a function that's written in terms of y or y dash or y double dash. It's just a function in terms of t. Okay. Well, let's look at what we've got here. So we've got the second derivative. Okay. We've got the first derivative, and we've got some function involving t. But we haven't got a y. We haven't got just a general y function like we had up here. Okay, so in other words, what we've got here is no y. So in other words, the original function is missing from this equation. Well, then if that's the case, then we can reduce it down to a first order. And we can reduce it down to a first order by being quite sneaky. So if we let some new variable, some new function, let's call it v, equal the first derivative. This is a bit like with A-level when we were doing hidden quadratic. So say, for example, if you had something like x to the 4 plus 2x squared plus 3 equals 0, and you're asked to solve that. Well, you first of all look at it and think, oh, the highest power is 4, that's going to be really difficult to solve. But if it's, let's say, something like a equal x squared, then that implies that x to the 4 is just going to be x squared, okay, so therefore we end up with a squared. So in other words, we can convert this into a normal quadratic just by saying a squared plus 2a plus 3 equals 0. That's exactly the same thing we're doing here, except instead of it being with kind of quadratics and, nice quadratics, we're dealing with differential equations, so we're dealing with derivatives. So in other words, if we just let v equal y dash, okay, then that implies that v dash must equal y double dash, because if the derivative of y is v, then the second derivative of y must be v dash. Right? So therefore, if we just replace it into our original function, so in other words, if we replace it into this thing here now, we end up with y double dash, which of course was v dash, just v dash, okay, plus y dash, which was just v, so plus v, and that's still equal to e to the minus t. Look, That now is a first order differential equation. Okay, and we can go about solving it in sort of any way you like. So in actual fact, this is a differential equation where we're going to have to use an integrating factor, right? Because if you like, there's a hidden there's a coefficient in there, the p of t coefficient in front of the v. So with integrating factor, we have y dash plus p of t. This is the general form equals q of t. So p of t y times q of t, and the integrating factor is found by looking at this coefficient of just our function. So we say then the integrating factor mu is e to the integral of this coefficient in front of our function, in front of y. So therefore, in this case, mu must be, our p of t is 1, right? Our p of t is 1 because it's kind of hiding in front of the v. Okay, so it'll be e to the integral of 1 with respect to t. Okay, so in other words, it'll be e to the t. Okay, so that is our integrating factor, and then it's just a case of solving it, using the integrating factors. That's nice and easy. So in other words, what we're saying is that the derivative with respect to t of, we just multiply by mu right the way through this equation, okay, of mu times v dash, and effectively the way that we use the integrating factor, we can just consider it as that just kind of, there's a cancellation which happens, which means that term effectively just disappears, and so what we're left with is then just mu e to the minus t. Okay, so we've got that thing going on. Oh, sorry, there's no dash there. Yep, because this thing is basically just d by dt of, dv by dt. So when we multiply through by mu, we can multiply through by mu, so we can stick the mu in there. It's just like a fraction, basically. Yeah. It's not a fraction, but we can treat it as a fraction. Okay. And so we end up with this. And so in other words, what we're saying is that, where mu is e to the t, what we end up is e to the t times v equals e to the t times e to the minus t. Okay, well that is just a bit like saying e to the minus t. Okay, it's just power law, so it's just 1 over e to the t, right? Because we're raising it to a negative power. So it's 1 over e to the t, so therefore what we've got here is e to the t times 1 over e to the t. So in other words, it just cancel off, because it just cancels to 1, okay? So in other words, what we just end up here on the right-hand side is that. So when we integrate, we end up with e to the t times v equals the integral of 1 dt. Well, the integral of 1 dt is just going to be t plus some constant of integration, let's call it c1, okay? And then if we just rearrange to find what v is on its own, so v is just equal to t plus c1 over e to the t, and actually what I'm just going to do is I'm going to write this e to the t as e to the minus t, like we did up here when we converted it back, because we're dividing by e to the t, so I'm just going to write it as e to the minus t, and I'm just expand this out. So this is e to the minus t times t plus c1 e to the minus t. So this is what we end up with for v. But remember, what was v? V was equal to y dash, yeah? V, where are we? V was equal to y dash. So in other words, we don't want to find what v is, we want to find out what y is. Well, that's nice and easy. So in other words, what we're saying here is that y dash, not just, v is equal to that, but what we're actually saying is that y dash is equal to that. So we've got e to the minus t times t plus c1 e to the minus t. Okay, so in other words, this is d, if you're not familiar with, or you're not really that comfortable with that notation, all that basically means is dy by dt, right? So in other words, what that means is that if we want to find y, we can just integrate this thing times t plus c1 e to the minus t dt. And I'm actually going to leave you to integrate that yourself. I could integrate this second term directly, because that's just going to be, or I can integrate this second term quite easily, because c1 is just a constant, so effectively it's just the integral of e to the minus t. Well, I can think about what's the derivative of e to the minus t, and it should be minus e to the minus t, so that's almost what I've got there. If I just consider it as the integral, take this constant out the front of e to the minus t dt, that's, the derivative of e to the minus t is minus e to the minus t, yeah? Minus e to the minus t. Well, that's almost what I've got there. I've almost got that right-hand side, except there's no minus there. So if I stick a minus there, then I'll just stick a minus out the front. Two negatives will just cancel out. It's just a negative times a negative, so I'll get a positive back. So that's the same thing as what I've got there. Okay, and then I could just say that is equal to minus c1, okay, e to the minus t. I can just say, well, if the derivative of e to the minus t is that thing in there, then the integral of that thing in there must just be e to the minus t. Okay, so that's quite nice and easy. And just don't forget your integration constant, so plus c2, let's call it. But this thing, the integral of this thing, is going to be a little bit more tricky. So all I've just basically done is just split this integral up into two parts. So I've got the integral of this one out, but this one's a little bit more tricky, and we're going to have to use integration by parts. Remember what the integration by parts formula is? It's the it's the integral of u dv, okay, must be equal to uv minus the integral of v du. And I'm actually going to let you do that yourself, okay, because this isn't a video on integration, okay. You should be able to do that. If you can't, there's plenty of resources out there where you can find it out. And if you do that yourself, so you find the integral of that thing, personally I would let u equal t, okay, because then that will just differentiate to 1, okay. So I'll just end up with 1 here, and I'll just end up with v, and whatever. It's not bad, but basically what you should end up with is that y is equal to minus t e to the minus t plus c1 e to the minus t plus c2. Okay, and that is your final answer. That's your final answer. And actually, you can double check that it works just by putting it into this thing. Or where is it? No, this thing, sorry. This thing up here. Because that's just my variables. This thing up here, if I put it into this thing, it should work. Okay, so in other words, when I find the derivative of it, find the second derivative of it, put it into this equation, I should just get e to the minus t. Okay, and that's fairly easy to verify. So this is your final answer. I'll leave you to kind of finish that off.